This is problem number 6 from section 3.4. I assigned numbers 5 and 7, the odd ones, but this is a good example. I'm going to work this one and hopefully it'll explain how the others are done. First part is finding eigenvalues, and these are set up, we're in the section where the eigenvalues are supposed to be complex, so sure enough, using our characteristic equation leads us to the characteristic polynomial, and I find in this case that we have complex eigenvalues of the form minus a half plus or minus the square root of 15 halves, the square root of 15 over 2i. Okay? And it is the eigenvalue that tells us everything about the behavior of the system. So the next question asks you if it's a spiral source, spiral sink, or a center. And if you look on page 305 of the text, you'll see, as I did in class, that these decisions about whether we're moving in or out has to do with the real part. If the real part is negative, we'll be spiraling in. If the real part's positive, spiraling out. And if the real part is 0, we will simply be periodic, some form of an ellipse, or maybe even a circle. In this case, the real part is negative, and so we have a spiral source. Since a is less than 0, it implies that our solutions will be spiral sinks. All solutions will approach the origin. The next question is asking you about the period of these rotations, of these oscillations. And just to remind you, for both sine and cosine, they have a natural period of 2 pi. When there's a number like b in the argument, so cosine of t has a period of 2 pi, cosine of bt has a period of 2 pi over b, or a frequency of 1 over the period b over 2 pi. So in this case, our period is 2 pi over the square root of 15 over 2, or 4 pi over the square root of 15. And our frequency is just the inverse of the period, so I won't write it, but it would be square root of 15 over 4 pi. The next question is the most interesting one, really, because I'm going to go to another page in a second, but really, if we're spiraling in, let me erase that quickly, just draw 2 pictures here. If we're spiraling in, we have 2 ways that we can spiral in. We can spiral in clockwise or counterclockwise. And so a solution could start, let's say, on the x-axis and spiral in towards the origin like this, moving in a counterclockwise direction. No, I'm sorry, this is clockwise. I apologize. Oh boy. This is clockwise. Yes. No, this is counterclockwise. What I said was correct. Okay, this is counterclockwise. So are we spiraling in this way, or are we going in a clockwise manner, something like this? Okay? How do we decide? Well, it all comes down, and it's a very easy question to answer, by looking at the coefficient matrix, because this is the matrix that determines the vector field. And so maybe I'm going to go to the next slide. The easiest way to answer the question, and it is a very easy question to answer if we have clockwise or counterclockwise rotation, is to ask the question, I like to pick a point on the x-axis. So, for example, if we pick 1, 0, so let's assume that this is 1, 0. I'll call 1, 0 right here, right? And 1, 0. Let's say that's 1, 0 right there, okay? So what's happening if we're in a counterclockwise rotation at 1, 0 is that at this point the vector field should be positive. I'm going to draw that in red. The vector field should be moving upward when we're at 1, 0 if we're going in a counterclockwise direction. Similarly, if we're going in a clockwise direction, the vector field should be pointing down. Now, we could certainly experience, depending on how these are drawn, I'm trying to draw these somewhat circular, but if they're drawn as ellipses, which they could be, I'll draw one more picture up here, and for argument's sake, I'll draw it counterclockwise. So here too, suppose we have something that's spiraling in as an ellipse oriented this way. I want you to observe that on the x-axis, when we pass through the x-axis, in this case, the x component is positive, but the y component is also positive. As opposed to, I guess I need to squeeze in one more picture over here. Oh, change my color back. One more picture over here. Again, I'll draw it, I will draw it in a counterclockwise. So this is rotating like this. And I'll draw one more, but in this case, I'm going to have it oriented this way. So it's spiraling in this direction, and here I am on the x-axis, and in this case, here's my direction that I'm moving when I cross the x-axis. I'm indicating this. It's very important to see that in this case, yes, we're moving, well, our y component is positive here, as our y component is positive here, but in this case, our x component is negative. In this case, our x component is positive. But in both cases, this is an example of counterclockwise rotations. Similarly, in a clockwise manner, the one consistent thing is that the y component will be down. The x component might be a little to the left, might be a little to the right, but the y component will be negative. And so I simply pick, I didn't want to do it in red though. I'm going to erase that. I just put in 1, 0 and see what it tells me. 0, I do the matrix multiplication, I get a 0. Well, this is a nice case because it'll be very clear. I get 0 for x, and I get a -2 for y. Okay? But typically I want to point out that typically the x value might be positive or negative. It doesn't matter. I'm just paying attention, in this case, when I'm on the x-axis, of what the y component is doing. Since the y component is negative, I realize, as the answer to part D, that we have a clockwise rotation. Okay, I hope that helps. Good luck.